Welcome everybody to another application session from Neuro Research. I'm Srijit here, and in today's session, we are going to focus on phonons and the applications. So, briefing about phonons in condensed matter physics, a phonon is a quantized unit of a vibrational energy that arises from the collective oscillations of atoms within a crystal lattice. So, for example, if you imagine atoms in a solid connected by springs, when one atom moves, it displaces its neighbors, creating a ripple effect that propagates through the entire material as a wave. So these waves of atom displacement are what we call phonons. So actually, what are the characteristics as an intro? First, quasi-particle. So while not fundamental particles like electrons or photons, phonons behave like particles in many ways. So they have a definite energy and momentum. So the phonons are not the vibrations of single atom, but rather a collective synchronized motion of many atoms in a crystal lattice. So bosons can be considered as phonons. So they have an arbitrary number of phonons which can occupy a same quantum state, which is important for understanding their contributions to thermal properties. Then dispersion relation. So this relationship between a phonon frequency and its wave vector is called phonon dispersion relation. So this is typically plotted as phonon band structure, showing the frequency or energy in the y-axis and wave vector along high symmetry directions in the Brillouin zone on the x-axis. And then speaking about acoustic modes, these modes corresponds to atomic displacement where neighboring atoms move in phase at long wavelength. And then optical modes, so these modes involve atoms within the unit cell vibrating out of the phase. So their frequencies are generally non-zero at gamma point and are often observed in infrared or Raman spectroscopy. So the number of optical branches depends on the number of atoms in the unit cell. And then speaking about the dynamical stability, the stable crystal structure will have a real or a positive phonon frequency. The imaginary or negative frequency indicates a dynamically unstable structure, meaning it can be spontaneously distorted into lower energy configurations. So the applications using AMS band on phonon calculations. So from first principles like DFT based methods are incredibly powerful for predicting the wide range of material properties and phenomena. So thermal properties like heat capacity. So phonons are primary carriers of thermal energy in non-metallic solids. So phonon calculations are essential for accurately calculating the vibration contribution of heat capacity as a function of temperature, then obviously thermal conductivity. So while more complex, for example, often requiring enharmonic calculations, phonon dispersions provide a fundamental input for understanding how heat propagates through a material. Materials with flat phonon bands or strong scattering generally have lower thermal conductivity, which is very crucial for thermoelectrics. And then speaking about thermal expansion, phonons contribute to thermal expansion through enharmonic effects, where the average atomic positions shift with the temperature. And then speaking about free energy and entropy, the thermodynamic quantities crucial for phase stability and chemical reactions can be calculated from phonon density states. So these are actually the basics related to phonons. And then speaking about structural stability and phase transition, so dynamic stability, as mentioned, the absence of imaginary frequencies is the entire Brillouin zone confirms the dynamical stability of the crystal structure. So if imaginary modes are found, it indicates a structural instability. For example, a ferroelectric distortion. And speaking about phase transitions, phonon calculations can help predict and understand temperature or pressure induced phase transition. For example, displacive transitions where a soft mode or drives like a phonon mode whose frequency approaches to zero can bring structural changes. And speaking about spectral calculations, IR and Raman spectroscopy, as I mentioned earlier, phonon calculations predict the vibrational frequencies and selection rules, which modes are IR or Raman active, allowing for direct comparison with experimental spectra to identify implies phases, chemical bonds, and impurities. And then speaking about inelastic neutron scattering, the experimental technique directly probes phonon dispersion curves, and theoretical calculations are vital for interpreting the complex spectrum. And then how we can use AMS band to this picture. So how phonon calculations can be, practical with AMS band. So AMS band has a powerful DFT code within the Amsterdam Modelling Suite, specifically designed for periodic systems, offers a powerful capability for phonon calculations. So first I need to point out that first principle basis. So band performs phonon calculations from first principles using density function theory, which means that it requires only atomic positions and types as input without empirical parameters. So this allows for high predictive power. And methods for force constant calculation, the analytical density functional perturbation theory. This is the more efficient and accurate method for phonon calculations. So I'm just briefing the theory behind all these things. So it calculates the response of electron density to small atomic displacement, directly yielding the interatomic force constant. And then the band's analytical phonon capability is a significant advantage. This method is generally faster and more precise for obtaining full phonon dispersions. And obviously, I have taken an example of a silicon crystal. I have selected this typical example for showing up the optimization and through how we can do this elasticity and phonon. 1 minute. Phonon and elastic tensor. So while selecting this silicon crystal from database, we have already created a video that how we can form, build crystals surfaces in AMS in one of our previous videos. So I'm not going into that right now because it will take some time. So once the crystal has been generated here, so this is actually the periodic view. So once it is generated, we will go for the geometry optimization, just enabling the phonons. And before that, just I have enabled the lattice optimization parameter, and then the properties phonons and elastic tensor. So I have just enabled the phonon calculation here in this interface with the calculation of the phonon density of state and phonon band structure. And after performing the calculation, the observation of what's the result, I would like to show you the band structure. So this is actually the band expected phonon dispersion band structure. So I have taken a face-centered cubic crystal lattice. So energy versus a path. So the phonon dispersion curves from this visualization can calculate and visualize the phonon frequencies along a specified high symmetry path in the Brouwer zone, providing the insights into wave propagation. And phonon density of state. 1 second, let me show you that what is the phonon density of state here. So speaking about phonon density of state, it computes the phonon density of state, which represents the number of vibrational modes at each frequency. So you can see the energy. So the density of state is crucial for calculating the thermodynamic properties. And obviously the thermodynamic properties from the calculated phonon density of state and band, the band automatically computes key thermodynamic properties such as internal energy, free energy, entropy, and special heat capacity as a function of temperature within the harmonic approximation. So this is actually a general concept. All these things will be briefed in our next video. So speaking about the visualization tool, just now I have shown you that how we can visualize the band structure and AMS movie through AMS movie. So it provides an integrated visualization tools to plot band structure, density of state, and even animate individual phonon modes. So these are the different steps which I have taken care for doing these calculations. And in summary, phonons are fundamentals to understanding the dynamic behavior and thermal properties of materials. So AMS band, which is a DFT based analytical tool, is excellent platform for accurately predicting and analyzing these crucial properties, contributing significantly to material designs and discovery. So in the next part, I'm going to brief you the analysis which covers the thermodynamic properties and the other important uh, you know features that can be shown with phonon through band. Thank you for now. We will see you in the next video. And for more information, I request you to kindly subscribe our channel and our LinkedIn page. Thank you.